So the problems I'm about to go through are really some pretty fun problems. Specifically, what I'm going to do is I'm going to give a little bit more attention to what this limit means. Right? We had the limit as x approaches 0 of sine x over x, and that was equal to 1. Right? So here's the catch. These limits don't always have to be going towards 0. Right? What's important and I don't really know how to write this on the screen. You're going to have to listen carefully. In order for this special limit to apply, there are some conditions, right? The first condition, and maybe I could just write these down, the first condition is that these two things have to be the same. They don't actually both have to be x, they just both have to be the same, right? So first of all, the argument on the top and the expression on the bottom need to be the same. Now the second thing is, this limit here doesn't have to be going towards 0. What's important is that whatever this is going towards, it needs to be making this thing turn into 0. So again, whatever this limit is approaching, it doesn't have to be 0, but whatever this is approaching, it has to be making these two identical things turn into 0. So I've got some examples of this. We're going to spend a little bit of time on this, but these are sort of good, exciting problems because it feels a little bit like magic. I'm weird. So my first example, evaluate the limit as x approaches 0 of the sine of 3x over x. Right? Now remember, there are two requirements for our trick to work. Right? In order for our trick to work, first, this and this have to be identical, and second, this thing has to be turning them both into 0. So is my first requirement met? Are those two things identical to one another? Well, the answer is no. One of them is a 3x and the other one is an x. So the question is, how can we fix that? And something to recognize is there's nothing I can do about that 3. And like you can't, factor out the 3 from inside of the sine. Sine and cosine are like the overprotective parents of the mathematics world. Like if there's something inside that you can very rarely get that thing out of there. You can use some of the wacky trig identities to do it, but it's more work than it's worth. Okay? So my better bet would be, is there any way that I could put a 3 on the bottom? And there absolutely is. If I just multiply the top and the bottom of this by 3, my limit would be the limit as x approaches 0 of 3 sine of 3x over 3x. And you'll notice now, hey, this now is the same as this. All I would have to do now is sort of, do the trick we did in the previous video, where I'm just going to take this 3 right here and kind of pull it aside. Like I'll pull it out front so that I can see that there are two component pieces. There's the 3 that's in the front, and then there's the sine 3x over 3x. Right? Now, because these are the same, and because 0 is turning them both into 0, and what I mean by that is imagine plugging 0 into these things. When you plug in 0 for 3x, it turns into 0. Because of that, the special property applies to this, and my limit here turns into 3 times 1, which is 3. Okay? Here's my next example, right? Evaluate the limit as x approaches 2 of the sine of x minus 2 over x minus 2. So, first question, is the argument inside of here the same, identical to what's on the bottom? The answer is yes, they're absolutely both the same. Right? Wonderful. Now, is this limit causing them both to turn into 0? Well, yeah, sure it is. If I were to try and plug in 2 here, I would get 0 and 0. These two identical things are both being turned into 0. Because of that, I can apply my special limit, and this limit turns into 1. And we're done. Now, you may find this one a little bit more complicated. It's sort of similar to the previous one, but in this one, again, we sort of start from the beginning, right? And I suppose to really start from the beginning, every single time we do a limit, we're supposed to try plugging in the number and see what happens, right? If I plug in 2 here, if I attempt to evaluate for 2, I end up with the sine of 4 minus 4, which is 0, over 0. Now, some people make the mistake of saying, oh, sine 0 over 0, that's 1. Not always. Sine 0 over 0 just means I don't know what it is, I need to try harder. Right? So now I look at it and I say these things aren't the same. Is there a way that I could make them the same? Now remember, there's nothing I can do to the x squared, like that's stuck there. Right? But what could I do to the x minus 2? What could I do to this problem to make those things the same? And sort of think about what you know about factoring, think about what you know about polynomial multiplication. Like, try and give yourself a minute, if you need to think about what you could multiply to the top and bottom to make those things the same. Hopefully you recognized that if you multiplied the top and bottom both by x plus 2, right? If I did that, I would have the limit as x approaches 2 of the sine of x squared minus 4, and then, times x plus 2. I'm not actually going to bring that in. I'm going to just sort of leave that one off to the side. The x plus 2 on the bottom, though, I'm going to bring in. These two things on the bottom multiply to give me x squared minus 4. And just like that, in one special, straightforward step, these things are the same, so they're identical. Are they both turning into 0? Sure. As x gets closer to 2, this gets closer to 4 minus 4, which is 0. Because of that, these things here, this is my special limit, this turns into 1. Times, so the question is, how do I do this limit over here? Well, remember how we handle all limits. We attempt to evaluate for the value we're given. When I attempt to evaluate for 2, I'm going to get 2 plus 2. That gives me 4. And so this limit is 4. Alright, I have one last example here, and to be honest, this one's probably not even fair. You guys haven't even seen limits as x approaches infinity. I'm actually going to formally talk about that in a couple days. But for now, I'm hoping that we can use this just to sort of think about it. I felt like this problem fit well here. Think about your steps, right? Your first step is what? Your first step is, are these two things the same? And they are, so we're in good shape there. The second question is, are they both turning into 0? Right? As x approaches infinity, are those things turning into 0? And the answer is yes. There's a couple ways to think about that, and I don't want to spend too much energy on it right now. One of them is to think about the graph of 1 over x. 1 over x looks like this. As you approach infinity, these values are getting closer and closer and closer to 0. That's one argument. The other way of thinking about it is thinking about what do fractions mean? What does 1 over 4 mean? Right? Well, 1 over 4 means you take one thing, you cut it into 4 pieces. Right? What does 1 over 10 mean? Well, 1 over 10 means one thing cut into 10 pieces, or smaller pieces. What does 1 over infinity mean? We're not even allowed to do that. But 1 over infinity means take one thing, one pizza, and cut it into infinitely many pieces. It means that each piece is basically 0. So because of that, this is one of our special limits, and this limit is 1.